everyone. I am Dr. Kuljeet Kaur, Associate Professor in Chemistry, School of Natural Sciences. Today I am going to discuss about nature of bonding in organic reactions. This is the very first unit of your subject organic reaction mechanism 1. So we will discuss the content about delocalized chemical bonding and type of delocalization first. Then we will discuss what are the effects of electron delocalization, orbital picture delocalization, conjugation, cross conjugation, hyperconjugation, applications of hyperconjugation, and tautomerism. So first of all, what are localized electrons? The electrons that are limited to a particular region are generally called localized electrons. Means the electron which is confined to a particular region. So the localized electrons, they are conformed between the two atoms or belong to a single atom, while some electrons are not conformed to a single atom or a bond. So the electrons which are bound between the two atoms or to a single atom, they are known as localized electrons. And the electrons which cannot remain confined to the two atoms, such electrons, they are known as delocalized electrons. And these electrons neither belongs to a single atom nor are limited to a bond between the two atoms, but are shared by three or more atoms are known as delocalized electrons. We can take an example of methane, for example CH4. It is having 4 sigma bonds. So each covalent bond is made up of 2 electrons. So these sigma electrons are confined between carbon and hydrogen. So these electrons are localized electrons. But if we will take the example of carboxylate ion over here, the pi electrons, they are not localized among only one oxygen. If we will shift the negative charge of this oxygen towards the carbon atom, the double bond, pi bond, it will shift it towards the oxygen. Means the upper oxygen will now get the negative charge. So these pi electrons, 2 pi electrons, they are not localized only on one carbon and one oxygen atom, but they are delocalized on these 3 atoms, that is 2 oxygen atoms and 1 carbon atom, right? So in the third structure over here, where I have represented 2 pi electrons with the dotted structure. So these are the delocalized electrons. Now, delocalization in a chemical bond can be carried out in different phase and in different systems. We can have 3 types of systems. One is isolated system, second is conjugated, and third is cumulative. So what is isolated system? Isolated system is the delocalization of electrons occurs in those compounds in which double bonds, they are separated by more than a single bond. Examples are given on the right hand side. This is the example of isolated double bonds. Here 2 double bonds, they are separated by 2 sigma bonds. So such systems, they are known as isolated double bonds. Second is conjugated system. In conjugated systems, there are alternate single and double bonds exist. For example, this is the structure, that is 1,3-butadiene. Here 1 double bond, then single bond and double bond is present. This is what is known as conjugated system. It is an example of 1,3-pentadiene, Then the cumulative system, if double bonds, they are present on the adjacent carbon atoms, for example in 1,2-dipropene. Such systems, they are known as cumulative systems. Now what is the effect of this electron delocalization? Now we can have the example of alkanes and alkenes. We know that in alkanes we are having only single bonds, that is the sigma bond, but in case of alkenes we are having double bonds also. So alkanes are having the longer bond lengths of sigma bond, but in case of alkenes we are having shorter wavelengths. When in a compound single bond is present that is larger, its bond length is 1.54 angstrom. But in case of double bonds, we know that double bonds they are shorter in length, its bond length is 1.34 angstrom. It is the case when the bonds are localized. But if we are taking the conjugated systems, for example benzene is there, we know in case of benzene we are having 6 pi electrons, and those 6 pi electrons they are not confined between particular atoms. Those 6 electrons they are delocalized on all the 6 carbon atoms. So in case of benzene, the bond length is neither 1.54 angstrom nor it is 1.34 angstrom. It will remains intermediate of single bond as well as of di bond, means it remains in between. It is having intermediate bond length which is lesser than the single bond and larger than the double bond. Whether it is a double bond of the benzene or it is a single bond of the benzene, it is having the same bond length, that is 1.39 angstrom. The second effect of electron delocalization is stability of dienes. If we compare two pentadienes, that is 1,3-pentadiene and 1,4-pentadiene, we are able to see in the diagram that 1,3-pentadiene, as it is having the conjugated, it is a conjugated system, the pi electrons are delocalized, so it is having the energy of 224 kilojoules per mole. But in case of 1,4-pentadiene, the two double bonds they are not conjugated with each other, so the system is having the higher energy, that is 250 kilojoules per mole. So with conjugation, the stability of the diene increases and energy decreases. That means the energy difference between 1,3-pentadiene and 1,4-pentadiene here is 28 kilojoules per mole. That conclude, as the conjugation increases, stability increases. Next is the acidity. Delocalization also increase the acidity. We can compare the carboxylic acids and alcohol. Because of delocalization of these pi electrons, in case of carboxylate ions, right, the carboxylic acids they are more acidic than the alcohols. Now, what is the fourth effect of delocalization? That is the stability of carbonium ion. Now, we know that in case of carbocations, if conjugation is there in the carbocations like allylic and benzylic carbocations, the stability increases than the primary carbocations. Why so? Because if we are watching the allylic carbocation over here on the upper right side of the slide, we are able to see that this carbocation, it is having double bond in neighboring of it. That double bond can contribute its pi electrons to stabilize that carbocation. That means it can reduce its positive charge, right? It can disperse this positive charge on 3 carbon atoms. That means it is increasing the stability of the carbocation, because we know that the factors which increases the dispersal of positive charge is increasing the dispersal, increasing the stability. Similar is case of the benzyl carbocation. Here also this positive charge can be stabilized by the 6 pi electrons of the benzene ring, as a result of which this positive charge get delocalized over all the ortho and para positions of the benzene ring, and we are getting different resonating structures, and that's why this benzylic carbocation is stable than the primary carbocation. So we can conclude that delocalization, it increases the stability of carbocations, and similar is the case of dipole moment. Dipole moment also increases due to the delocalization of electrons, because more will be the charge separation, more will be the dipole moment, and more will be it involved in the resonance, right? So here I have given some examples where we can conclude that as the double bond pi electrons, they are participating in the dispersal, means they are giving its electron towards the carbon carrying the positive charge, stability increases. The first carbocation, it is stable than the carbocation which is mentioned on the right hand side, which denote primary carbocation, right? And here in the second position also, this carbocation which contains the allylic double bond, and it is stable than the secondary carbocation. Then similar is the case with the benzyl carbocation, which is stable than its primary carbocation, and here we are having two allylic bonds, and it is also stable than its allylic carbocation, which contains only one double bond. So if we are representing towards the orbital, we are going to discuss the orbital picture delocalization. So we can represent a carbocation in this way, that is, we are having sp2 hybrid orbitals and one empty p orbital which is having the positive charge. So if we omit these hybrid orbitals, and instead of that we can write these three bonds with the methyl groups, and we can draw the empty p orbital. So we can represent in this way, and here we can show the delocalization of the pi electrons. First is the example of butadiene, where first and second pi bond is there. Now this, because it is a conjugated system, so the pi electrons, they are dispersed on all the four electrons. So we cannot represent with the orbital all the times. So simplify it, we can represent these structures in this way. Here we can show the dispersal of the pi electrons with the dotted line on all the carbon atoms, and similar is the case with the carbocations. And from the delocalization, now we are moving towards the conjugation and cross conjugation. A system or a molecule which has alternate single and double bond, now we very well know that that system is known as a conjugated system, and 1,3-dienes are very good example of the conjugated system. And we know that in conjugated systems, overlap of p orbital allows the electrons to be delocalized over a larger portion of the molecule, thus lowering the energy to the molecule and making it more stable. The conjugation effect is at a maximum when the axes of the orbitals, they are aligned in a parallel style, because this allows a maximum orbital overlap. Notably, an atom that is capable of donating a p orbital can be the part of conjugated system, and thus the atoms, whether it is with the lone pairs or it is containing a free radical, positive charge, that is carbocation, and negative charge, it can be the part of conjugated system as represented in all these examples. In the very first example, it is of free radical, right? So this free radical can also participate in the dispersal of charge, and ultimately this positive charge odd electron, it can disperse on all these three electrons. And if we are taking the example of second example, the positive charge similarly can disperse on all the three carbon atoms, and Third is the example where lone pair can participate in the delocalization of the electrons in the conjugation. And fourth is the example where carbon ion can participate in the conjugation system. So these are the four different ways how the conjugated systems contains the delocalization of electrons. Now, aside from that, conjugated compounds, they can be acyclic, cyclic, or mixed. We are having examples over here. For example, B, it is a conjugated system, that is a 1,3-pentadiene. And if we are talking about the cyclic conjugated systems, example A, that is benzene. Here is a cyclic conjugated system, naphthalene, furan, anthracene. These are the conjugated systems which are cyclic in nature. And third one, C, is the example where we are having cyclic as well as acyclic conjugated system present in the same example. Right? Now conjugation is broken only when there is sp3 hybridized carbon atom is there. In conjugated system, sp2 hybridized carbon atoms must be there. That is why we can take the example of 2-cyclohexenone and 3-cyclohexenone. 2-cyclohexenone is more stable than 3. Why so? Because in 2-cyclohexenone, 2 double bonds, they are present in conjugation. Right? But in 3-cyclohexenone, we can see that these two bonds are separated from each other by 2 sigma bonds. So there is no possibility of the conjugation or delocalization of pi electrons. That's why this 3-cyclohexenone is less stable than 2-cyclohexenone. Now after the conjugation, we are having the cross conjugation also. Cross conjugated systems are the systems where we are having 3 double bonds, right? And in that particular system, 2 double bonds, they are in conjugation with the third double bond, any third double bond, but they are not in conjugation with each other. Here I have given 2 examples. In the very first example, as we can see, A and B double bond, they are in conjugation to each other. B and C also, they are in conjugation to each other, but if we are discussing about A and C, they are not in conjugation to each other. So such systems, they are known as cross conjugated systems, and the phenomenon is known as cross conjugation. Now what is the importance of this cross conjugation? We know about the electrophilic substitution reactions, right? If I am having an aniline and I am doing the bromination of aniline, which is an electrophilic substitution reaction of aromatic compounds. We know that nitrogen is having a lone pair of electron. That electron, nitrogen can donate to the benzene ring and increase the electron density on the ortho and para positions of the benzene ring. So because the benzene ring, it is having the more electron density now, and if we are doing the bromination, we will get tri-substituted product over here. But if we want to do that reaction in a controlled manner, means we want to synthesize para-bromoaniline instead of tri-bromoaniline, we have to control the reaction. And how we can control the reaction is, we can do the acetylation of this NH2 group. Means if we will introduce acetyl group over here on the aniline, we can induce the cross conjugation here, because this carbonyl group is also electron withdrawing in nature. It will withdraw the electrons of this nitrogen towards itself. So now the tendency of this nitrogen, it decreases to give its electron to the benzene ring by resonance. So then we'll do the bromination, we will get only one mono-substituted product of acetanilide, right? Then afterwards, we can do the deacetylation of that particular compound, and we will be easily get the para-bromoaniline. So we can use the cross conjugation in this way, right? So the next part is the resonance, right? Resonance, we know that for some compounds we can represent the structure by a single Lewis structure, right? Or we can say the dot structure. But there are some organic compounds whose structure cannot be represented by single Lewis structure. So for many molecules we can say two or more dot structures are also possible. To explain the structure and physicochemical properties of such covalent compounds that could not be represented by a single structure, Heisenberg introduced the phenomenon of resonance. Especially resonance is a situation in which more than one possible structure can be written for a species, but not the true structure at all. For example, the acetate ion, right? So acetate ion we cannot represent with a single structure. We can write it with more than single structure, that is this negative charge can be dispersed on all the three atoms, right? So we can write the two structure for acetate ion. Such structures are known as resonating structures. And if we are taking very good example of resonance is benzene, we can also represent the benzene with more than single structure, right? Because its pi electron cloud is dispersed on all the 6 carbon atoms. So the number of structures we are representing, these structures are known as resonating structures, and the actual structure is known as a resonance hybrid over here. The characteristics of resonance are all the atoms in the molecule taking part in resonance must be coplanar, right? No sp3 hybridized atom should be there. All the atoms should be sp2 hybridized. The resonance structures, which are also known as contributory structures, they are only the imaginary structures, and the resonance hybrid is the real structure of that. Due to the resonance conjugation fact, the bond length in resonating structure exhibit equal values, as I explained to you in the earlier slide also, that in benzene all the bond lengths are equal, that is 1.39 angstrom. In different resonating structures, the position of the nuclei must be the same in all the structures, and the total charge should also be constant. The resonance hybrid has the lower energy and has the greater stability than all the contributing structures. So greater the resonance energy, greater is the stability of the molecule. So those structures have small contribution where the negative charge means if the same charge present on the adjacent atoms, the same charge will repel each other, so that structure will be less stable, right? And secondly, if the negative charge is present on more electronegative atom and positive on the more electropositive, that structure will be more stable in resonance as compared to the structure in which electronegative carries the positive charge, right? So here we are having some examples of the resonating structure like vinyl chloride, ozone, and phenoxide ion, right? So with this, I am concluding the today's lecture. Today we discussed about the delocalized chemical bonding, the concept of conjugation, cross conjugation, and resonance. I hope you people are clear with today's lecture. In the next class, we will discuss about hyperconjugation and tautomerism. Thank you very much.